Good afternoon. My name is Mattia. I'm a PhD student at Stockholm University. And I know you're tired. It's the third day and last day of the conference, but I promise it's going to be a light talk. I will present some pedagogical tool to teach students data reduction with Not. I should say that this project has been financed by the Department of Astronomy at Stockholm University with a grant earned by Professor Mattia Sirressi, who has been designing the notebooks together with me. I will just use the arrow. So this pedagogical tool is actually used for a course named Observational Astrophysics 2 at Stockholm University. This course provides a hands-on introduction to how astrophysical observations are performed, both at optical frequencies and radio frequencies. And for the optical part, it includes remote observations at Not, to be specific with the alpha spectrograph, of course followed by the data reduction and analysis of the acquired data. So the motivation behind the development of this new tool is this one. It has been a struggle for many students at Stockholm University to use IRAF to understand data reduction. Instead, with the newly developed tool that is based on Python, the students can go through every single step of the data reduction interactively and play around with the intermediate products. So this tool is based on Jupyter notebooks. If you don't know what those are, I will show some examples later. And here's a couple of quotes from students, one at a time when IRAF was used. Observation 2 with IRAF was a real nightmare. And one from this year, actually. I was working on the AlphaSC workbooks. It worked well. Many thanks for creating them and making our lives easier. So I can quite proudly say that this is the second year that the Python notebooks are used successfully for this course. So just to say, what I mean here is that IRAF is not the best tool for pedagogical purposes, of course. This is the structure of the material that the students go through. It's 7 notebooks, one for each step of the data reduction. Workbook 1 is for the bias subtraction. Workbook 2 is for the flat normalization. I call them workbook because it's really hands-on kind of work the students do when they use these Jupyter notebooks. So we have workbook 3, which is the extraction of a 1D spectrum from a window that has to be defined. Workbook 4 is wavelength calibration. Workbook 5.1 is the extraction of the spectrum of the standard star. 5.2 is the flux calibration. And workbook 6 is the coaddition of multiple spectra of the same source. So let me just have a quick demonstration of a couple of workbooks. I will start with the number 1, the bias. Okay, so for those of you who have never seen a Jupyter notebook, those are some online documents that are divided up into multiple cells. For example, here in the first cell, you can just type some text, normal text. Here you have the title, and at the beginning of each workbook, I just explain what is the step that the student will work on. So here, what is the bias, and why do we need to subtract it from the other frames, and how this is gonna be done. And in other cells, one can write lines of code, and each cell can be run individually. So here in the second cell, I just import the packages, Python packages needed. Then To start with, I list the file names in the data directory. Then the student can go through the bias frames in the data directory and have a quick check. So it's going to access the fits file using the header keywords, and basically they will print the file name, the exposure time, the frame size, the number of pixels, and some image statistics like the mean value of the pixels, the median, the standard deviation. And this for every single bias frame, just to check if there is some frame that has something off or weird. Then a student might wonder how a bias frame looks like, so they can plot it. Of course, they can do that with DS9 as well, but since they're working on such a document, it's fairly simple to do it here. And they can play around with the color and the stretch. So after that, they can combine the bias frame into the master bias, and they can choose one of the two options implemented, the mean or the median, and they can compare the two. And finally, they will subtract the master bias from the other frames, right? So again, they use they access the fits file, and here they print the image type of the file that has been corrected, and the name of the new fits file created with the _b extension. All right, so let me quickly go through another workbook. So this was the bias subtraction is the first workbook. It's fairly simple, and it gets a bit more complicated as the students go on with the next workbooks. So here it's about extracting the spectrum, and again, I start with describing what is going to happen, and everything is well commented, so it should be clear for the students to understand. So here I list the science objects, and the student will choose one to work with. Here they can plot it, and they can again check some basic information like the image type, make sure that it's an object, observational mode, and history, so they make sure that there's been bias subtracted and flat normalized. And then the first thing to do after that is to find the source along the spatial axis. So here they can plot the profile of the source. And here you see there's this broad signal, which is the galaxy, and a more narrow, higher peak signal, which is a supernova, which is actually the target of these observations. So they want to define a window here, and they can do that using the so-called continuum tracing technique. So defining a window as a function of the dispersion coordinate, y in this case. So here is the green band is the window for a certain dispersion coordinate. And they can also interpolate the window's properties as a function of the dispersion coordinate. You can see that the source position here, it's pretty constant as a function of y, so just a couple of pixels of difference. And finally, they can extract the spectrum, and they can also decide to do it much more easily with a fixed window and extract the spectrum and obtain a slightly different result. So this is the idea of the workbooks. I hope you got a clear impression of what it's like. And just to conclude, the last slide, I just want to say that this tool is public on GitHub, so everyone can download it, and it can be even personalized and expanded to tackle your own scientific problem if you wish. Of course, this has been designed with a purpose of teaching students, so you might want to implement some more sophisticated things, but For example, now a student is working on a workbook number 7 to estimate the uncertainties on the flux densities. So yeah, this is it. I'm happy to answer questions if you have.